Hey, this is Will Sutherland doing Lab 1 report on the tape lab. So the purpose of this lab was to find the charge of two pieces of tape of equal charge that is required to levitate one of the pieces of tape. So in the results, we found that for the observed charge, it was negative 1.914 times e to the negative 8 coulombs required, while the computational model was the charge of negative 1.2 times e to the negative 8 coulombs. And this is basically an excess of 1.196 times e to the 11th electrons. So the fundamental physics principles were Newton's third law, where the net force of a system is force equals mass times acceleration, and the also with electric fields and Coulomb's law, basically where the electric field is equal to Coulomb's constant, which is 8.99 times e to the ninth, times the vector pointing from an observation location to the charged particle, where that charge is q. And so this is how we did our experiment. So we found the length of the tape B, which is this top one, to be 0.21 meters, the mass of it being 2.1 times e to the negative 4th kilograms. And basically the starting heights were 0.3 meters for tape A and 0.34 meters for tape B, which was a 4 centimeter difference. So in our system is tape A and tape B, while the surroundings is everything else. In calculations, we found that the magnitude of the force due to gravity and related it to the magnitude of the electric force on B to find the overall charge, which was, as you can see there, negative 1.94 times e to the negative 8th coulombs, and there was an excess of electrons, a lot of them. Okay, so this is coding, part 1. So basically we set up the same sort of stuff, the initial conditions, as well as some of the arrow stuff. We also defined the electric field function here, basically the same thing as before, just doing that, and then found the electric field of the first one and printed that. And then after that, we found the net force using Coulomb's law, as well as with the gravitational force, as well as there was the applied force on tape A, which was what we used to hold up tape A. So basically we summed all those to find Fnet and printed that. And then after that, I set up a while loop. So while the net force on B was less than 0, it would go through this loop. So basically, through every time, every iteration would add 1.6 times e to the negative 19th times a billion electrons. So basically, just adding a bunch of electrons until we get to a force where the net force is 0. And so you can see here, the net force is in green and it's going to 0, as then these are the electric forces, they are equal, and this is the distance between them is still 4 centimeters. So again, the observed model versus the computational model, they were very similar results. Basically, the observed model, we assumed that the U-tape had an even spread of excess electrons along the entire piece of the tape, and the computational model assumed there was negligible air resistance and friction. And for both, we assumed that they were point charges, where each tape had the same magnitude of charge. So some other questions we have is, so for the what if, so if protons and electrons switch their charges, fundamentally nothing would actually change, because the concept of positive and negative charge is just that, a concept. So the relationship between charges would not change. It would just mean like just treating the meanings of those words differently. And so it's important not to touch the charge or try not to touch the charged objects or the tapes, because the more you touch them, the more the electrons are transferred either to or from your hand, making that object less charged. So in conclusion, we assume that tape A and so for possible error, we assumed that tape A and tape B had the same magnitude of charge. They could have had different magnitudes of charge that would have changed the overall, I mean, the charges of what we found. Also, other forces like air resistance, friction could have been involved, which again would have changed the results. And so, yeah, that's basically it. Thank you very much.